Hello students, welcome to another video of my channel. In today's video, we are going to discuss about one more application of Gauss law, that is the electric field intensity due to a thin spherical shell. Now, a thin spherical shell is nothing but a hollow sphere. Okay, for that hollow sphere, we are going to find the electric field intensity, and that sphere has a uniform charge distribution of Q. So here we consider a positive charge Q which is distributed uniformly on the surface of this hollow sphere. The radius of this hollow sphere is R, right? So we are going to calculate the electric field intensity due to this hollow sphere at 3 points. One point which is outside the surface of the sphere, another point which is on the surface of the sphere, and the third point which is inside the surface of the sphere. So we are going to calculate the electric field intensity due to this thin spherical shell which is uniformly charged. First of all, let us calculate the electric field intensity at a point P which is outside the surface of the spherical shell. For this, we consider a point P which is at a distance small r from the center of the spherical shell. If O is the center of the spherical shell, then the distance between O and P is small r. Now, we have to calculate the electric field intensity at the point P due to this spherical shell, and the distance of this point is r from the center of the sphere. So we will get a value of electric field at this point. Now, first of all, let us consider another sphere which is a radius small r. At every point of this imaginary sphere, the electric field will be the same. The electric field will be the same at every point of this imaginary sphere. So what are we required? We are required to calculate the electric field intensity at every point of this sphere. So what do? We first consider a small area element ds on the surface of this sphere. We consider a small area element ds on the surface of this imaginary sphere, right? So for this hollow sphere, which is the direction of the electric field? Now, as you know that for a spherical shell or for a sphere, the direction of the electric field is always radially outwards. So for this spherical shell, the electric field will be radially outwards. This will be the direction of the electric field. This is the direction of the electric field, perpendicularly outwards or radially outwards. Similarly, this is the small area element ds. What will be the direction of the area vector for this small area element? The direction of this small area element will be perpendicular to the surface, which will also be radially outwards. The direction of the area vector ds will also be radially outwards. So what we find here is that the direction of electric field E and the direction of ds will be the same. What will be the angle between the electric field vector and the area vector? That will be equal to theta equal to 0 degree. So what we have here is theta is equal to 0 degree, since the electric field is parallel to the area vector. Now, in order to apply Gauss law for this surface, what do we have to do? We'll have to calculate the electric flux. So what is the electric flux for this outer sphere? So we get the electric flux to be integration of E dot ds. What is E dot ds? E dot ds is nothing but E ds cos of theta. What is the angle between E and ds? That is theta is equal to 0 degree. In this case, we have seen that the electric field vector lies in this direction and the area vector for this element also lies in the same direction. So what is the angle between these two vectors? The angle is 0 degree. So here we have cos of 0 degree. The cos of 0 degree is 1. So what do we get the electric flux? The electric flux is integration of E ds. Now, since the electric field is constant at every point of this outer sphere, we have seen that the electric flux is the same at every point of the outer sphere. So what do? We keep E outside the integration. If we integrate ds, what do we get? If we integrate ds for this whole surface, then what are we going to obtain? We are going to obtain the surface area of this outer sphere. Okay. So what is the value of the area for this outer sphere? That is 4 pi r square. So what do we have? The electric flux to be E into 4 pi r square. Next, we are going to equate this field of electric flux with the Gauss law. So finally, what we are going to calculate is the value of E, that is the electric field at every point of this sphere, or we can say the electric field at any point which lies outside the sphere at a distance r. So at this point we are going to apply the Gauss law. How? Let's see. According to Gauss law, phi E is equal to Q by epsilon naught. Again, what we have found out for this sphere, phi E is equal to E into 4 pi r square. So we can equate these two quantities since the left hand side is the same. So if we equate these two quantities, then what we can find out? We can find out the electric field associated with this surface. Okay. So what is the electric field at every point of this surface? That is E equal to Q by 4 pi epsilon naught r square. Now if we put the value of 1 by 4 pi epsilon naught as K, then what we finally have? We have the electric field to be KQ divided by r square. Now see, this is nothing but the electric field due to a point charge. Okay, if we calculate the electric field due to a point charge Q at a point which is at a distance small r from this point charge, then what is the value of electric field? That is equal to KQ divided by r square. And similarly, here also what we have found out that the electric field due to this sphere at any point which lies outside the sphere at a distance r is equal to KQ divided by r square. So what we see here, we see that the value of electric field for this shell and the value of electric field for a point charge at a point P which is at a distance r from the charge is the same. Okay, so we draw an important conclusion from this part. So finally what we have got is E equal to KQ divided by r square. This is the electric field due to a point charge at a distance r. So in this case, at the point outside the sphere, the electric field is as if the total charge of this sphere, that is Q, is concentrated at the center. It appears as if the total charge of this whole sphere is concentrated at the center of the sphere, right? Next we move on to find the electric field on the surface of this spherical shell. So we are required to find the electric field at the point which lies on the surface of this sphere. Now if the point P lies on the surface of the sphere, then this distance will become equal to capital R. So what is the value of R? R will be equal to capital R. So we have to find the electric field. The electric field is KQ divided by R square. In this case, R is equal to small r is equal to capital R. This distance will be reduced to capital R. So what we have? The electric field to be KQ divided by capital R square. This is the maximum value of the electric field. So what we can conclude is that the electric field is the maximum if the point lies on the surface of the sphere. Thirdly, we will try to calculate the electric field at the point which lies inside the surface of this shell. So we consider the point P to be inside the surface of this shell. Then what will be the electric field at that point, right? So you are already aware of the fact that the electric charge always resides on the surface of a conductor. Electric charge never resides inside the conductor. Okay, so for this conductor, if this is a conductor, then electric charge will be equally distributed or uniformly distributed on the surface of the conductor, and there will be no charge inside the surface. So what do we have? The total charge inside the surface to be 0. Okay, so there is no charge inside the surface, therefore Q is equal to 0. So in this case, what will be the value of electric field? Equal to KQ divided by R square, that will become equal to 0. So what we have seen is the electric field inside the surface of a conductor or at a point which lies inside the surface of the conductor is 0. So now if we draw a graph for the electric field versus distance from the center, then we will get a graph something like this. We will get a plot something like this. Say in this diagram, what is the value of electric field up till R? Here capital R is the radius of the sphere. So from this point, from the center up till here, the electric field is 0. So we have found out the electric field to be 0 inside the surface. So the value of electric field for this part will be equal to 0. We will get the maximum value of electric field on the surface of the sphere, as we have already seen. So we get a maximum peak at the surface of the sphere, that is at R equal to capital R. Beyond that, the electric field will keep on reducing with it is inversely proportional to the square of the distance. So as R increases, the value of electric field will keep on decreasing. Okay, so this is what we have found out the electric field intensity due to a uniformly charged thin spherical shell. This is also a very important topic from the examination point of view, so kindly study it properly. Thank you.